What do skiers, roller coasters, and a certain crime-fighting spider all have in common? They all need to get from point A to point B in the shortest amount of time. But what is the fastest path between 2 points? This was the exact question proposed by Johann Bernoulli in 1696, the Brachistochrone problem. Bernoulli's indirect solution to this was clever, as it bridged the worlds of classical physics and mathematics. Bernoulli chose to represent the motion of a particle using light, enabling him to use Fermat's principle of least time, which states that a beam of light traveling between 2 points always chooses the path that takes the least time. Fermat's principle shows that when a beam of light passes from one medium to another, it changes direction or refracts according to Snell's law. Snell's law states that the sine of the angle the beam makes with a line perpendicular to the boundary, divided by its velocity in the medium, remains constant. By the law of conservation of energy, the loss in potential energy of the particle is equal to the gain in kinetic energy. Thus, the velocity of the particle, v, is proportional to the square root of the distance the particle is falling, h. Now imagine a system of infinitesimally thin layers of material stacked on top of each other, and a beam of light following Snell's law passing from one layer to the next, where the velocity of light in each layer is proportional to the square root of h. As the distance from the top increases, velocity increases, so the sine of the angle the beam makes with the line perpendicular to the boundary must increase for Snell's law to hold true. This produces the Brachistochrone curve, the fastest path between 2 points.